Okay, guys, welcome to another episode of Cuda Education. Um, this video is a follow-up to the first buffer device address video. So I created a whiteboard edition of this video, basically going through the whole process of using buffer device addresses to access data memory assets in GPU memory efficiently. So instead of doing the descriptor set process or the descriptor process in Vulkan, we go through GPU pointers, 64-bit GPU pointers that point directly to the memory in the local GPU, so that we can manipulate it and do all of that good stuff. A lot of moving parts in this video, so it's important for you to pay attention. Yeah, so we have the .cpp file, which is, CPU side file, source code, if you will, the main source code. And then, of course, we have our shaders, right? Specifically the vertex shader, okay? So we have our source code and we have our shaders, right? Shaders are GLSL for this particular source code, okay? So yeah, we just want to do, a quick run through of the basic things that we covered. So this is a picture of the whiteboard edition, sort of the full picture. So we have enable buffer device address features, enable buffer device address features. So that's just in general here and also in the shader here, right? So write data into GPU device memory using memcopy, and then also map into GPU memory, right? So, and we have, for this step right here, we have specific flags: VK buffer usage, shader device address bit. This is to tell Vulkan that we plan on querying for the pointers to the GPU memory, and we plan on using the pointers, in the shader, right, in our processing. We also have VK memory property host visible coherent bit as another flag in this buffer creation step, and we use this flag to basically tell Vulkan and sort of, the powers that be, that this buffer, this memory that we're working with, it's going to be visible both by the GPU and the CPU. And this is important because the CPU will be rapidly updating what is in memory because of rotation calculations, right? So let's just stick with this first step right here before we get in too deep, right? So we'll go back to our code. Let us run our code, right? And when we run our code, we basically see two boxes that are rotating, okay? And, if we turn off animation, the boxes don't rotate. And if we turn it on, it rotates, right? This process is because of the updating of the GPU memory by the CPU, right? So the CPU is updating. Now, how this actually goes about rotating, I misspoke. you know, and it's basically tinkering with the model projection view settings in order to see the rotation, right? So we're not going to focus on the mathematics of the rotation. We just want to know that the CPU is updating the local memory in GPU and causing this to rotate. And of course, when we stop, we're no longer updating, right? And that's pretty much it. That's pretty much what this application does. But of course, there is a lot going on here. Okay, so let us we'll just do a simple thing. So, you know, here, this sample shows how to read data from a buffer device address, aka reference, instead of using uniforms. The application passes buffer device addresses to the shader via push constants, and the shader then simply reads the data behind that address. This makes stuff like descriptor handling a lot easier, as we now only pass around references akin to pointers and no longer need descriptors for buffers. See cube.verb for the shader side of things, right? So we'll get to cube.vert in a sec, but let us search for this memcopy thing, right? So there are only two instances of memcopy, right? So we're basically memcopying stuff over into the CPU side into the GPU side of things, right? So you know, basically, if we disable memcopy, the application still runs, but now we just don't see anything, right? We just don't see anything, right? So memcopy is what allows us to get stuff into the GPU, and then we're able to see it, okay? Let's see if we have map. Okay, so this map, so we'll see how many, so we have two maps, right? So notice that we have prepare uniform buffers and update uniform buffers. So let's go down to okay. So here we have our prepare uniform buffers. Now this map, note that we don't use this buffer for uniforms, but rather pass its address as a reference to this shader. So instead of uniform buffer usage, we use a different flag. So notice for the map, as I mentioned here, notice for the map, we have VK buffer usage shader device address bit, right, as one of the flags. That is to tell Vulkan that we plan on that the buffer's address will be queried and passed to the shader, right? And then we also have VK memory property host visible, right? VK memory property host coherent bit, right? So that basically tells, the powers that be, host visible coherent. It's basically telling us that the CPU is going to be able to see and access this buffer in the GPU, right? And remember, a buffer is like a memory block. It's like a container, right? That's all it is, right? So the CPU is going to be able to access all of this memory, access and update all of this memory that is part of, you know, the topic at hand. See, we also have another map. Note that we don't use this buffer. It's the same language, right? But again, for this buffer, so we have our scene buffer and our cube buffer, right? Notice that we have the same flags, right? We have the same flags. Now, I wonder if I take out the flag. I know if I take out these flags, it still works. But I know it still works if I take out the host card. No. Right, so it works. We're not even able to run, but yeah. So we query these two. I mean, we're gonna query the buffer addresses, so we have to put in those flags, right? So that's that piece of it. Okay, so we understand the mem copy and we understand the mapping, and we know with the mapping we have to flag it, right? So what the map is just a tunnel or a road that basically says, okay, the CPU and the GPU, the CPU has access to the GPU and can update the GPU memory and all of that stuff, right? So that's why on the map we have to put in these flags, because it's the buffer in the GPU memory. So we have to put the flag to say that yes, this buffer is going to be queried, and yes, this buffer is visible from the CPU side and can be updated from the CPU side, right? So that's this piece right here. All right. So we've kind of gone through that stuff. Now, I will admit that this is Vulkan's fault, not necessarily the author's fault, but all of these concepts are sort of scattershot between different functions, right? Which is why it's kind of hard to penetrate the example, right? Because it's a lot of things going on and they're going on in different places, right? But, we have the mem copy here, right? And we have the mapping happening here, right? Scene buffer and cube buffer, right? So I guess scene buffer is just like the general scene, and the cubes, of course, are the cubes, right? See, we also have this here, okay, for this guy. Right, but we're just focused on the mapping piece of it, the create buffer piece, right? Do I want to go through the rotation? So here is we're calculating rotation, the rotation piece here. I have tried to comment out pieces of it to see what would happen, but notice that only one of them rotates now, right? But when I comment, so X, Y, so even with animate, nothing rotates, right? And then Z, right? So Even with animate, nothing changes, right? So that makes sense. Now, if we uncomment X, let's see what happens. So now we have in one plane, there is a rotation, right? So, you know, I'm not going to get into the math of this, but basically, you notice one goes in, I guess, X, and then the other one goes in probably, I guess, Y direction, however you want to say it. So if we disable the calculation for the X and Y plane, we are going to get frozen cubes no matter what we do, right? And that makes sense because, I mean, nothing is being rotated in Z, so that makes sense, right? And then we just go back to normal just to make sure that we are in business, right? But I don't want to dive in too much into this calculation and all of that and why one cube is affected and not the other and all that, right? That's for a different day. Now, I believe if I comment out this last one, then the cubes don't even show, right? I'm not going to go down why this is the case right now. That is not the point of this discussion. But okay, so we covered rotation calculation, write data into the GPU device memory, rotation calculation, a mem copy and map, and then this is into the GPU. All right. Get device pointers to the data in GPU memory. VK get buffer device address KHR. So VK get buffer device address. So let's look at all the places that this is. So we have VK get buffer device address KHR, PFN. So we have a mention of it here, right? Then in prepare uniform buffers, we also have another mention of it. And seeing buffer device address, you know, we're rotating through the frames, but we're getting the buffer device address for the scene. And then I guess we're also doing it for the cube, okay? I think I did a tinker with this. I did a tinker with this. Did I? What did I do? Did I just set the I to one value? I did a tinker with this. I don't even remember now. But anyway, get buffer device address KHR, right? Notice that it's lowercase vk, right? So we're now trying to get the addresses. We're trying to get the addresses for this buffer here in the GPU, right? We're trying to get the addresses for the buffer. We need this extension function to get the address of a buffer so we can pass it to the shader. Right? So I'm going to guess that if I disable this, I basically get a crash. Right? Are you guys still with me? Okay, you guys are still with me. Yeah, basically I can't run this. It basically just crashes, right? Which I guess makes sense because we need to enable this feature. All right. VK get buffer device address KHR. This might be a specific to this application. I don't know. But we do, yeah. So we need this extension function to get the address of a buffer so we can pass it to the shader, right? I'll probably do another video talking about this specifically once I investigate, right? But yeah. But what I want to focus on is buffer device address. So right, we're querying for the addresses of the buffer. Okay, that's what we're doing. We're doing here. So that's that. Package pointers into a push constant strut. Okay, so now we're getting into push constant, right? So okay, so this sample passes the buffer references pointer using push constants. The shader then reads data from that buffer address. So remember how I kept talking about how there is package pointers into a push constant strut, right? So this is it here, live and in living color. So we have a strut called push constant block, reference to the global matrices, reference to the per model matrices, okay? So we have scene reference and model reference, right? We're gonna see this later in the shader also, right? So we have this block here. Let us continue. Prepare pipeline. The buffer addresses will be passed to the shader using push constants. That way it's very easy to do a draw call, change the reference to another buffer or part of that buffer and do the next draw call using different data, right? So I believe right, this is declaring during pipeline creation that you'll be using push constants, right? So this all of this logic here is basically letting the, upon pipeline creation, you're letting Vulkan know that you're going to be using push constants, right? And the stage flag is VK shader stage vertex bit, right? And that makes sense because notice that in the send the package over to the GPU using VKCMD push constants, we have this flag also VK shader stage vertex bit, right? So we're basically saying push constants are going to be used for, and the stage flag is for the vertex, right? We'll get into the shader stuff in a little bit, but we have to declare that we're using push constants to the pipeline. I don't really want to get into the details right now of that, but just know that this is the logic that we are concerned with as it relates to the pipeline and push constants. Is there anything else worth mentioning here? Instead of using descriptors to pass global and per model matrices to the shader, we can now simply pass buffer references via push constants. The shader then simply reads the data from the address of that reference, right? So we have this references block. Let me just go through. I just want to go through. All right, so let's start back over. So we have a strut called push constants block. Scene reference and model reference are in there of type VK device address. All right, that makes sense. In the pipeline, we declare that we're using push constants, and the stage flag is going to be the vertex shader, right? Because of this guy right here. No problem. And then we create another block called create another block called references, and inside of it, okay, right. So this is a signature or the general layout of the strut. All right, I got it now. I got it. Right, this is the general layout of the strut, of the push constant block strut. So, right, this is a signature or the general layout. You know, you guys who are C++ talk, you have better language than me. But this is basically the format of the strut, right? And then we create a strut here called references, and then the dot scene reference is going to be scene.buffer device addresses current buffer, right? Because we're looping through, the command buffer is looping through every instance, right? Here, we do the same thing for model reference. We have scene reference and model reference, right? And then we do VKCMD push constants, right? And that is this guy right here, right? VKCMD push constants. See, guys, I'm not lying to you. I'm not lying to you, right? So we create the strut, and then we basically push it over into the GPU, aka the shader, right? We push it over into the shader so the shader can access it, right? Notice that we include our references strut, which is the push constants block, right? And we also include VK shader stage vertex bit, right? Right. So we include that and we send it over to the GPU. I do want to... Yeah, this current buffer thing is another question that has to be addressed. But I believe this current buffer happens during runtime. Yeah, but where is it initialized? Anyway, all right, so this is where we push over our package into the shader, right? So this basically goes over into the shader, and we will discuss that in a bit. And this is all under the build command buffer, right? So you guys also have to sort of keep track of which functions these activities are happening in, right? So this VKCMD push constants operation is happening under the command buffer, right? So we send our addresses to the shader via the VKCMD push constants, right? Under the references strut, which is a push constant block, okay? And we load it up with here. Well, we initialize it here, and then we load it up here, and we load it up here, right? We have to loop for the cube because it's 2 cubes, right? So that is that. Now I do want to make sure right, so you see how we have our buffer device addresses here? Buffer device addresses. So we're pushing we're querying for the addresses using VK get buffer device addresses KHR. And we're putting it into the buffer device addresses for scene and also for cube, right? This is all under the prepare uniform buffers. Now, so right, under prepare uniform buffers, right? That's what we're doing here, under prepare uniform buffers. Now, so we're preparing here, so we're loading it up here. I just wish we had. Right, so we're loading it up here. And then in the command buffer, we are querying for the addresses. All right. Now, what I do want to find out is max concurrent frames. All right, let's not digress with that. But basically, we're loading it up here, and then in the command buffer, we're actually querying for them, right? And then we push the package over to we push the package over to the shader. Okay. So there's only one VKCMD push constants in the entire instruction set. Pass pointer to this cube's data buffer via a buffer device address. So instead of having to bind different descriptors, we only pass a different device address. This doesn't have to be an address from a different buffer, but could very well be just another address in the same buffer. Yeah. So let us now look at what's going on the shader side. So once we push the package over, now the shader should have access to our addresses, right? So let us look at what's going on over there. I remember we're only pushing it to the vertex shader, right? So this is the vertex shader. First thing you need to notice is that we do include the extension for buffer reference, right? Because we are using this device, the buffer device address, right? So we receive push constant, uniform push constant. So we receive the variables here. We receive the data here. Remember I said matrix reference, scene data, matrix reference, model data, right? So the first block is scene data and the second block is model data. And then basically we have our GL position. We have our calculate GL position in the shader, right? So we receive the data here, and then we calculate our GL position, right? So let us disable GL position. Remember I have to compile, guys. And then we'll run our code. If I disable GL position, our application runs, but I don't see anything because there's no GL position, right? So that's sort of the what we're trying to calculate, right? So when we have our GL position, we have our thing, right? All right. The other thing that we want to do is, remember I said that it's very important the order in which we ask for the data, right? So 1 and 2, right? If we start playing around with the order in which we ask for stuff, we're gonna get into trouble. So let me just, instead of doing it how it was done, I'm gonna do this. And I have to compile. And notice that the boxes disappear, right? Now my understanding, my hunch is that we do scene data first and then model data second, which is why I made it a point that we have 1 and 2 here, right? So 1 is scene and then model is scene first and then model second, right? So this VKCMD push constants, we're pushing it to our vertex shader. We're receiving it. Scene data reference. We're receiving it like this. And then we're using it down here. So notice that matrix reference scene data, which we use down here, equals push constants dot scene data reference. Matrix reference model data is push constants dot model data reference, right? And then once we have these variables, we use it here to do our calculation, right? And just to further demonstrate the importance of this GL position, I'm going to start to play around with the calculation. What was it that I did? I did... there was something I did. Was it this? Right, so we get, it's basically double the size, right? It's double the size of what it was normally, right? So when I take this out, I get our regular boxes, right? I don't know if this does anything. No, that just makes it blank. But yeah, I don't know if this does anything. Yeah. All right. So you guys get the drift. As homework, you guys can figure out why it changes the way it does because of this. Got to make sure I get back to what it was before. Okay, so we're back to normal, right? Okay, all right. So we've successfully passed in our data into our shader. Remember, the shader is on the GPU side of the equation now, right? So the shader is on the GPU side, and between this operation and this operation, we're able to, and this operation, of course, we're able to calculate our GL position. I'll probably have to do another video talking about the exact language of all of this. I don't really want to speak on it too much right now, but just know that we received our stuff because of this. Now, yeah, basically the application crashes. Yeah, application crashes because we don't have any data for the shader. All right, so that is that. We're back to normal. Okay. I know this was a rough video, guys. I apologize, but as you could see, a lot is going on. The purpose of these videos is just to ignite your guys' curiosity so that you can take it from there. Just some good housekeeping. Let us clear up some other things I had highlighted. First of all, we have our max concurrent frames situation here. And notice we have arrays and we're dealing with buffer device address and max concurrent frames. So that's just, you know, just doing some good housekeeping. Second thing is we do have our push constant block, and it's VK device address seen and VK device address model reference. This might be the reason why we expect scene and model here, right? So in the strut, the first thing is going to be scene and the second thing is going to be model, right? So it's probably a function of this strut right here, because that's how this sample passes a buffer references pointer using push constants, then the shader reads the data from the right. So global and per model matrices. So it might not necessarily have been, you know, 1 and 2 as I kind of mentioned in the previous video. It could be just because of this the structure of the strut that goes in to here. Okay, so that's the second thing. Third thing is we have to enable the buffer device address function, right? Feature, extension and feature. So we have to enable it here. Okay, we have to enable it here to basically let Vulkan know that we're going to be querying for these addresses. Also, this right here, all of this. Not sure what's going on with this misspelling, but you guys get the drift, right? As we said before, we have to let the pipeline know upon pipeline creation that we are going to be using push constants, okay? So remember, VK, lowercase VK, create pipeline layout, right? So all of this information is being captured into this call right here. And this call is so important, we actually have a VK check result as part of the call, right? Because we have to make sure that we have our pipeline, right? But you have to declare that you're going to be using push constants in the process, right? Next thing is that when we're creating the buffer, we actually have to tell Vulkan again that, hey, this buffer is going to be queried for the device, the device buffer device address, what have you. So we have to put that flag in, and then we also have to put in the coherent bit, right? So we have that there. Same thing here and here, right? Buffer related operations, right? But you guys have a better understanding of what's going on here. Of course, we have our rotation calculations, and then we do a mem copy into GPU memory, right? We create our first instance of the strut that we reference above. So we create the first instance, and then we load it up with addresses, right? So seeing that buffer device address current thing, we load it up with addresses, right? Load it up with addresses. And then we do our VK push constants. We cannot forget we cannot forget that we query the buffers. We query the buffers with VK get buffer device address KHR. Okay, we query for the addresses, right? Using this. So yeah, guys, listen. This code is only 320 lines of code, but it's a lot to digest. It's a lot to digest. There's a lot of things going on. I'm not going to act like it isn't overwhelming. As I said, as I learn, you guys learn. But this is just an initial attempt at plowing through the complexity, right? Vulkan is going to be Vulkan. There's no question about that. But again, I will say the reason why Vulkan does all this stuff is because it wants to give you control over everything and all that's happening. So, don't get discouraged. You could use this as sort of a guiding light in what's going on. This situation here with the buffer device address 1 and 2, it could be because of how the strut was designed. So that might be the reason why it behaves the way it does, right? But yeah, guys, a lot is going on, but this gives you a great template. And actually the author of the script actually encourages people to use his code as a template for whatever it is you're trying to do. Okay, just know that the shader, we have our source code, and then we have our shader that takes in stuff from the push constants and what have you. All right. So this is Cuda Education, guys. Thank you for watching. If you want to have these examples running on your machine, assuming you have a Windows machine with a Vulkan-capable GPU, you need to get tutorial number 1 and tutorial number 13. Now, this specific example is not ray tracing, right? So it's just a regular example. It's not ray tracing. So you will be able to run this if your GPU is Vulkan capable, but it isn't ray tracing capable. If you want to be able to run the ray tracing examples, you need to get a ray tracing capable GPU. For NVIDIA, that's the RTX series. I don't know about the other GPUs, right? But for NVIDIA, it's RTX series. Again, the buffer device address, you have to be careful with them. It's not advised for mission critical implementations. It's better to use a descriptor approach if you want to do, if you want to be on the safe side. Also, for like mobile devices and older hardware and stuff, the buffer device address feature might not be available. So you might run into problems with that. Also, if you're doing heavy memory operations and you're moving things around, or you have other applications doing stuff with the memory, it's not advisable to do it because the addresses might become invalid or what have you, right? So yeah, guys, I did not expect this example to be so involved. Honestly, it is for 300 lines of code. It's a lot going on. Valuable lessons learned. And again, the other thing too is that a lot of it is split up among different functions. So it's not like you have one block of code where everything is just going logically one to the other. It's split up across various functions. We have the prepare pipelines function where we have to declare the push constants. We have the prepare uniform buffers where we're querying for the addresses. Update uniform buffers where we're doing the mem copy and also doing the rotation calculation. We just have prepare, which is enabling a feature. We have the build command buffer where we are actually executing the VK CMD push constants. And a whole bunch of other stuff. But yeah, I'm almost an hour into this video. But I hope this video was helpful, right? I hope it's a start. Guys, this is just a start, every day is just an opportunity to learn a little bit more. And as we learn, we get better and better and better at it. Cuda Education is the best place to learn Vulkan. I still believe that wholeheartedly. You start with running code and you learn by tinkering with and observing the code that's running, right? And seeing when you change stuff, how it affects the application, whether the application crashes or it runs, but there's some other thing that happens visually or otherwise in the application. So anyway, thank you for watching. Have a great day. Like and subscribe. You know the deal, guys. Goodbye.